She's also the author of a forthcoming book, which you should all check out, called Transformers: The Definitive Guide: Applications Beyond NLP, Beyond Natural Language Processing. That's published by O'Reilly Media, and it's actually going to be an early release this Thursday. So urge you folks to check that out. And it is my great pleasure right now to hand you to Nicole Koenigstein. Nicole, thank you so much for doing today's talk.
My pleasure, and thank you for the kind introduction. All right, let me go ahead and share my screen. So it should be fine. Let me just show you shortly a bit of the agenda of what I want to cover today. So we'll give you just a little bit of basic language model landscape introduction so that they are all on the same plate, and then some introduction to LLM agents. And I will cover as of the topic of the talk, time compute. And with that together, research, this is then reinforcement learning based. And then something fairly new, what I'm doing in my research in my company is evolutionary code generation. And this is kind of a new paradigm, which I'm looking into right now. Right. So first of all, you might or might not have heard about the scaling laws and kind of related to foundation models. If you haven't, it's kind of fairly simple. So we have that extremely large models right now. In recent years, for billion, hundreds of billion parameters, and they are really large. And the reason why we have those large models is a couple of years back, actually, researchers from OpenAI found out that there is that kind of a scaling law. So the larger the models are, with more data, they tend to generalize better, and then they can perform better on that wide range of tasks without that specific fine-tune. So it adheres to a certain amount between compute you need and then the amount of data you need. And given that, also, I want to clarify before we move on some terminology, because sometimes it's that they got mixed up interchangeably, and I just want to make sure that it's kind of clear what we are talking or what I'm talking about. So foundation models are often mentioned, and some people might mistake this as large language model only, but in fact, foundation models is really a broader category or class for AI models. And it just means, like I mentioned with the scaling laws, that this is actually just trained on a vast amount of data. And because of that, they can learn different patterns. And there are even, and actually fairly good foundation models, transformer-based foundation models out there for time series prediction. And what actually happens is they can predict on a zero-shot basis, meaning without any training. You just give them the time series to predict. And if the time series is not that complex, like not in, let's say, financial time series data, they do already actually a pretty good job, and they get better and better kind of every day. So there are also improvements, as we have seen with the foundation models within the large language scape. And given that, I want to switch from the large language models to the instruction models. So we have just the basic large language models, and then we have that instruction fine-tuned models, which are under the category of language models, but they are specifically tuned with reinforcement learning to follow human instructions and be a helpful assistant. And then most recently, we got the next step, the next iteration for those language models. We have that, what is called reasoning models. And there's that underlying chain of thought, instruction going inside of them. And they are specifically trained with that kind of framework. And there are also different steps, which also involves training them with reinforcement learning manner to follow this internal chain of thoughts before they answer. And some models even can even go and like you can switch between the thought following and thinking path and modeling. So for instance, the Qwen tree, this implements that kind of different structure, and you can actually switch between, and you can even save computation in telling the model to have a certain barrier there. It has to stop thinking and just answering from the past thinking processes. Right, and this brings me to the LLM agents. So this is just to bring you again also on the same page of understanding. So I'm pretty sure most of you have already seen agents. And what you see here is, so one part is we have a user request, and then it gets to the core. And this is kind of that autonomous agent system. And here the LLM functions as the agent brain. So it kind of is the orchestrator and complemented by several key components, what you see here on my current slide. So we have maybe tools like calculator, retrieval augmented generation, a web search, code interpreters for writing code, and so on, like different even custom functionalities. Then usually what we have memory modules. Most of the time we have different memory modules. So you will see different ones later. Then I explain the evolutionary code generation. And then we have also planning modules, so meaning reflection, self-critique, so the LLM can either judge itself or it has an internal external judge, and another language model or a human. And then as with the reasoning models, we can have chain of thoughts and tree of thoughts, which are just other ways of guiding the model to have a bit of a better structural thinking. And yeah, these are just some other examples of different architectures of agents. So we have single agents and React agents, multi-agents, which can process different different tasks because they have like split it into kind of a team. And I will show you on the next, I think like the third slide or so, you will see the overview. And then reflection agents, which have an inflection loop, and I will show you this as well. And then multimodal, where you can have the processing of different modalities like tabular data, text data, image data, audio, video, and so on. And this is just for you to see the difference. So this is a single step agent on the one side, so just one step. So the agent or the LLM accesses just a tool and then does it and returns a result. Then with the React, which basically is reasoning and acting, if we spell it out, we have then an interaction and then thinking process. So we have that thought, action, observation loop. So this comes all together in guiding the model in doing the task at hand or fulfilling the task at hand. And yeah, this is the overview I mentioned just. So we have again the single agent on one side, then we have a so-called supervisor architecture, and then we have a hierarchical architecture. And why does that matter and why we want to differ both? So the supervisor is that kind of a simpler multi-agent setup there. The LLM acts as a supervisor for other LLMs, and it orchestrates the task at hand. So there comes in a prompt from the user, and maybe it's like they want to compute the weather. They want to, from the current temperature, from the weather, let's say in New York, since I'm in New York right now, and want then the square root for that. And then you maybe have an agent which is in charge of getting the actual weather information, the temperature, and then you have another agent being in charge of just doing computations at hand. So what the supervisor does, it gives it routes, then the task accordingly, and you can have this conditional or non-conditional usually. So if you use, for instance, a framework like LangGraph, you can have conditional actions. And this means that the supervisor itself decides which agent is in line next to fulfill that certain task. So in that case, with the weather example, the supervisor would first give it to the agent which has access to the internet, gets the current information about the weather, the temperature, and then this payload, so this information, will be routed to the next agent, which will then do the computation. And then it's done, the payload. So these computations will be then directed to the supervisor, and the supervisor will then end the whole loop and give the answer to the user. And for the hierarchical, it's kind of the same setup with the supervisor, but this is meant for more complex tasks, meaning you have a team of supervisors, and then you can have different things to do. For instance, you want to write a financial report. So as in a company, you have different people doing different things, and maybe even different teams coming together and do this. And here's the same. So one might do the research on some part, put it together, then you have a writing and an editing process and reviewing process, and this might be another team. And here it's the same. So if you have more complex tasks, it's better to split this into that hierarchical architecture for the agent. So that LLM, the supervisor, does not get overwhelmed and all the others well, not. So it's better to split the tasks more granular, better results. And well, why does this matter? Why do you want to bother with agentic systems at all and reasoning and so on? So here's a simple overview. So one side, you have a traditional workflow with predefined sequences. The flexibility is limited, the goal handling is linear execution. And then with the agentic system, what you actually have, like I explained, you have a dynamic decision loop. So depending on your agent architecture, we take the multi-agent setup with the supervisor and the conditional actions. So the LLM actually decides and gets kind of that autonomous behavior in a kind of a limited space, because you still define the agents and how they behave and what tools they can access. But in that framework, the LLM, the supervisor, decides which task comes first and then next, and when the whole task is finished, and it presents the final results. And because of that, of course, it's context aware, it uses tools, and it's also iterative and can be a self-correcting kind of system iteration. So the goal handling is not just the linear execution step by step, but it can be very well iterative. And I will show you some examples. So here we see the outlet of the React agent. So we're reasoning over iteratively over context. So we map the context to the action in that action space. And we have a policy where we update then the actions with the context, and we have the pods which are integrated into this contextual update. So the actions are the task-specific steps impacting the environment, and then we have that reasoning traces. And you can actually, depending on what kind of framework you're using, you can actually pretty easy make those pods visible to you.
Nicole, I'm so
yes.
sorry. I'm so sorry to interrupt you. If you could
No
maybe
worries.
speak up a little bit. A few folks are saying they're having a little trouble hearing you. So I don't know if that's possible.
Let me try and let me see if I can So yeah, this brings me to the reflection agent part. So I told you, like, you can have it iteratively and self-correcting and thinking. So this is actually what you're seeing on the current slide. So here, what we have that user request coming in. And then the first part, we have the so-called responder. This is an LLM, which accesses also tools, executes tools, and produces an initial response. Then what's happening is that initial response gets validated by the revisor. And this is another LLM which judges the output from that responder. And it does so by accessing different tools. Maybe it's RAG, maybe it's internet sources, and just external tools without just considering its own knowledge to validate the responder's answer. And it gives critics and information and citations how the responder has to refine the answer to actually match the prompt, the criteria from the user. And you can define how many times you want to do that recursive or that repetition. And based on that, you can have also matrix in how you want to improve the actual output from that reflection agent. And then we can go even a step further. So we can have also then an active evaluator and also the self-reflection of the model. So this is a very similar setup, and it's called reflection, and it's not a type, it's actually differently spelled to the other. And here we have an action based on the environmental state using that language model, and it's guided both by the current observations and the memory of past reflections. And then we have that evaluator, which assesses the actor's actions with the task-specific criteria. So you can have success or failure, or you can have very specific metrics, what you define according to the task at hand. And then you have a report for the feedback. And then the model can analyze the actions and get the feedback and store it into memory. So for the future decisions, it gets better. And this brings me really to kind of that combination between reinforcement learning and LLMs. So this is called the in-context reinforcement learning. And this is actually pretty interesting. But before I'm going to introduce you, I just want to mention here the explore-exploit trade-off, because this is kind of a very important paradigm within the reinforcement learning space. So what we do is, or what we're trying to achieve with that is, we want to have enough exploration to gather new information, but also have a good balance how we use that new information to improve actually our goal we're trying to achieve, so the performance at hand. So we want to try, or we try to balance the two out. And you remember I was talking about that foundation models and the scaling laws, and the more data, the better, and it can generalize better and so on. Well, there's actually right now kind of a movement bit back to having smaller models. And there was actually a paper released last year in August by DeepMind, and they looked into this called test time compute. So it's really going to the paradigm of thinking smarter and not just bigger. And why do we want to do this? So, of course, the problem is that the bigger the models, it's get more expensive to train them in the first place. So you have that billion parameter models, and it's very expensive to get them to that state. It's also the problem with the data curation. So what we do is we give the model more time to think. So the smaller model, more time to think. And why does this matter? Of course, smaller models, and we give them more time to think, so more compute as test time. So during inference, the reason is it can even outperform much larger models. Now I'll show you a concrete example for a comparison. And this is especially on complex reasoning. So this is very interesting because you can have faster inference, so better latency. So this means how fast the model can answer to the prompt. And you don't need to have that large GPU setups for your company. So I deploy in my company open source models, and it's a matter of if I need, for instance, 4 GPUs or even more, or just one. If I would run it 24/7 in a month, it's a matter of either 65,000 or about 8,000. So it very much matters how big the model is. It can be very, very costly. And the key idea here is instead of just taking the model's first answer, there will be used a strategy to explore multiple reasoning paths, and then we can refine that output. And it's kind of the very same if you think about it. If you, for instance, think you're in a quiz show and you need to answer right away, you just have a limited time. Let's say you compete against and someone else, you press a button and now you have immediately say the answer. But if you have a bit of a time to think, let's say 2, 3, 5 minutes, then you might evaluate different things and you come up with a way better answer than the original first one. And it's the same with the models. You give them more time to process, more time to think, more time to evaluate and reason and come up with a better answer. And this is how it looks like. So this is the overall system setup for test time compute. So we start with a problem, and then it goes to the language model, and then we have that search strategy. And I will show you some search strategies in the following slides. So what we then do is we generate intermediate steps. So here's just an example with a math problem to an LLM, and then it creates partial solutions. And then the intermediate steps get a derivation and the process, and then we have what is called the process reward model. And that estimates the probability of each step to eventually reach the correct final answer. And then it scores. And based on this, we choose then the final solution, the candidate solution, which is ranked, and then we produce the final answer. And this is the slide I was mentioning for the comparison. So here you see the 8 billion instruction model from Llama and the 70 billion instruction model. And comparison for the next iteration, so 3.2, 1 billion, and 3 billion. And as you can see, they really outperform the bigger ones because they got more time to think. So number of generations per problem, the more they got compute, the better they were. And this is from the paper I mentioned. And yeah, just as a side note, you don't have to screenshot or anything for the papers and things like this. I will share the slides with you, so you can directly access the link for ease of use. And yes, so what you see is we basically look into how we validate the difficulty of a problem. So what they actually did is they looked not only into, does it matter to give them models more time to think, but what they found out is that depending on the problem difficulty, we need to use different strategies and we need to allocate different test time compute accordingly, given the difficulty level. In principle, this is pretty straightforward if you think now about it, because for the same for us humans, if a problem is more difficult, we need to think longer, we need more time to come to that solution eventually. And here's the comparison. So these are different methods for doing that scaling, that test time compute. And we see here really strategies like best of n, better on harder problems, and beam search is better for those more difficult things. And we have also other algorithms going in that direction and being more of a complementary strategy to beam search, because it doesn't perform always that well. So there is something called diverse verifier tree search. And what it does, it expands the initial set of the beams into independent subtrees. And then for each subtree, it selects the step with the highest process reward model score. So we have that process reward model again, which I showed you on the previous slide. And then we generate new steps from those nodes and select then again subtrees and so forth. And then we just repeat until we exceed or reach the final results. And this is the next iteration kind of over this. And this is specifically interesting because it leverages something called KV cache nodes. And why is this interesting or important? So let me maybe first explain what KV cache is. So for text generation, code generation, we usually use autoregressive generation. And for doing so, we need to, look up and create those tokens. And this comes from the computation of the key value and the query. So what we can do with that KV value caching, this is just a clever trick that at inference time, the key and value matrices to calculate these generated tokens are stored in memory. And this means that the subsequent tokens are generated from memory, and we only need to compute the keys and values for the new token. So we don't have to compute everything anew, but we store the previous one and have just the new ones generated. And this means that we can speed up the inference from KV caching. But the problem is, of course, we need more memory and so on. But if you have a good GPU set up and the newer ones are really kind of optimized in that direction, you can really leverage this, and you can really implement it and leverage like it does here with efficient tree search. And what we then do is for that given set of trajectories, you have again, we use sampling weights based again on the Revard model scores. We formulate an integer programming, linear programming, and then select the subset of the trees to maximize the total reward while minimizing the number of unique KV cache nodes. So we are taking care of that. Then we prune the trajectories, reduce the caching of the sharing, and use that to generate the new trajectories. So we take this into account. So we optimize the KV cache and retain just a certain amount of nodes and new trajectories. So we are actually more computational. And one of my favorite algorithms when it comes to mixing reinforcement learning and language model is actually language agent tree search, and LATS for short. And this was actually the very first algorithm which leverage both or different paradigms within language models and reinforcement learning. So what they did is they incorporated the reasoning, the acting, and the planning to enhance really the language model performance. And it's based on Monte Carlo tree search. And the other algorithms I showed you previously are also tree search based. And the key features here really are that we have a language model-based value function. So we replace that traditional reinforcement learning training with a specific language model-based value function to leverage that in-context learning. And that in-context learning, I mean, I'm pretty sure you did use ChatGPT or another instruction model for interactions, and you certainly notice that if you are guiding the model, give it feedback, and it learns from that stream of back and forth. So that is that in-context learning. And what we also add is the self-reflection for exploration. So remember the exploitation trade-off I mentioned earlier. And then what they also have is an external feedback for adaptive problem solving. So we could have a so-called human in the loop for guiding the model, give additional feedback. And this is how it looks like. So we have first the selection, the expansion, the evaluation, then we simulate, we backpropagate the values, and then we have that reflection. The reflection is to learn actually from the past failures, so that if we have something similar, that we don't make the same mistake again. And let me walk you through for each of that. So here's the Monte Carlo tree search and how it's working. So we start from the root node, we traverse through the tree, select the node based on the upper confidence bound, which is applied to the tree, and I will show you this just in a second. Then we have that expansion. And if the selected node is not terminal, we expand, generating a child node from the possible actions we have. Then for the simulation, we run that random simulation from the node to the estimate value. And then what we do, we backpropagate the simulation results back up the tree, updating the node values along the way. And then, like I said, when the trajectory fails, we use the feedback for self-reflection to adjust then the future decision, refining the search because we avoid repeating the same mistake and improving then the overall strategy with that. And this is the upper confidence bound applied to the tree, so UCT. And what we do here is the value for the expansion is selected by the next iteration. So the UCT of a child node state is calculated by the estimate of the node, the visit counts, the count of the parent node, and then we have an exploration rate we add. And the backpropagation in LADS is similar, fairly simple. So the return is used for updating the nodes along the path, and we have the old value function and replace it then with the new one. And I just wanted to show you, these are just a couple of slides, how fairly easy actually this is to implement in LangGraph. And for everyone interested in running the notebook and seeing the code in action, just let me know. I can share the GitHub repository with you of that LADS implementation. So yeah, we see we have the upper confidence bound, the backpropagation. We have that initial response we do, then we expand tree, so it's all fairly straightforward. It's not a lot of code. And then we extend with the children and with the candidate, and you see also here the reflection. So if we want to have, for instance, more external validation or human feedback, we could put it into this part. And then we just generate all the candidates and have that finally. Fairly straightforward. And here, this is just the very simple and same kind of setup how you generate kind of that graph and agent set up in LangGraph. So you add the nodes and the edges. And you see here actually the conditional edges I mentioned before. So we have the conditional edges for start and for expand. And here it then decides based on the current state of the loop if we expand or not. And here's just a very simple example to show you how this works. So what I did was I put in the question to look up the probe and risk factors of Uber and Lyft and what company performs better, and it got the instruction from me that it should use concrete numbers to inform the decision. So I don't have the whole output from the model because that would be way too much for the slide. But what you see here is you see the score. You see the node if we found actually a solution. What kind of reflection was done, the critic. So remember I showed you the slide with that reflection part and the critic. And this comes also into the whole setup with LUT. So we have also these parts. So it gets the critic, and based on this, we can do the next iteration and do the refinement. And based how we have the scoring of the overall result, it returns then the score for this. And just a side note here, so Monte Carlo tree search is actually really a natural fit for reinforcement learning in financial markets because unlike more traditional Q-learning, this struggles in partially observable settings, and Monte Carlo tree search-based approaches follow more on the fly exploration and adjustment of the trees, and this is really helpful, particularly in real-time trading where you have like the change rapidly. And this brings me to what I'm researching right now, so the evolutionary code generation. And beyond that Monte Carlo tree search, reinforcement learning can be combined with an evolutionary code generation. So we use the LLMs sort of a mutation operator. And here we bring it together also with agents. And that what will be done is here we iteratively refine, for instance, trading models, optimizing strategies, and this can be real-time based on the market signals. And part of that is something what is called MapElite. And the extreme distinction between the past algorithms I have shown you is that with MapElite, this is non-greedy. So Green Search, all the other tree search, these are greedy. And with MapElite, we have direct diversity because it doesn't explore randomly. It does it more systematically across a diverse behavior of needs. So as you see it here, so we have a selection of parents. So these are the needs, and then we have that different behavioral dimension you want to have. So for instance, each agent or team is that kind of species, so we can draw actually that parallel. And then we have those descriptors, and this means maybe risk or latency or market style. And then that MapElite algorithm is that kind of selective pressure shaping the ecosystem of that strategy. So we have that parent strategies, let's say two complete function strategies, and then we merge them, creating child strategies, and these improve because we are merging and improving these iteratively through the evolution. And you can compare it pretty much to, we have it with DNA. So for the DNA, we have the genes which tell the body how to do things. And here for that evolutionary code, for the strategies, so we have, for instance, an archive of strategies with different traits like risk, latency, market size, like I mentioned before. Then we have that phenotype, which means how the body grows based on that certain information, and that goes the same for that evolutionary code. So we have those offsprings with the better or best performing traits out of that previous strategies, like the parent strategies. And how can this achieve? So again, this is a bit more of a more complex setup, what you saw before, but again, we have just the LLM at the very basic stage. So it orchestrates and is a point of entry. And now it comes kind of all what you've seen before together. So you have that feedback and the refinement. We have an internal part. So we have that reasoning, we have that reflection, we have the test time compute. Therefore, we have the next step with the learning. We might also retrieve more information, let's say from RAG or from other sources, like from the internet, and bring this together. Then we have that external part. So remember, I said the strategies can be refined based on the market feedback. So we have that code written and get the market into this. So it's plugged into the real-time system, you get the information, and based on the information, it gets back to the language model, the code will be adjusted, and the strategy will be therefore adjusted. And also what you can do is you can, of course, then have that dialogue with a human, give feedback, get this external feedback, like I said with Vlad. So you can have that external reflection part, giving more information how things should move or behave differently. And I mentioned also when I showed you the overview slide of that agent that we have different memories. So here we see procedural, episodic, and semantic memory. So procedural, we have an agent code, we have the model, LLM, and semantic, we have a strategy code base you're leveraging from. And then we have that episodic where we have a relevant code, we have examples, we have the chat history, and this gets then factored all in. And then again, the LLM orchestrates all of it. We have coding agents sitting there. These are just language models, agents in an agentic setup, validating each other, like I showed before with a reflection, now just for coding. And then they produce different proposals, and based on all that external and internal feedback, they improve and they test, run back tests, run tests with the market, and then they improve the next iteration. So what we then eventually end up with is we have candidate agents, which are evaluated not just by reward, but by behavioral descriptors. So we kind of determine where we map them and place and compare them. So we can have trait frequency, volatility, preference, portfolio correction, and so on. So the system maintains really a map of different and best performing agents or strategies, so to speak. And with that, this is not static anymore. So we've gone even a step further. We not only have an agentic context-aware workflow, we have really kind of something which is refining on the go. And maybe some of you have heard about Darwin-Gödel machines. So it goes in that direction. So where we have the Darwinian evolution and the Gödelian self-improvement. So you have that feedback loop, you have that validation, and based on that, you have evolution and refinement and self-improvement. So you can have the prompt-based recombination of prior successful strategies. You can have embedding-based selection. You can implement, like I said, the human feedback to influence also future generation of such strategies. So with that, you have a continuous adaptation in the system, even after post deployment. And never then you have just one single agent or strategy or language model adapting in isolation. You can also have an interaction between so-called agent populations. And this encourages then the population on competition. So really like you have with the evolution in the past, so the survival of the fittest, you can actually have that evolutionary pressure here as well. So therefore, the agentic systems are able to reason, reflect, evolve in market with real-time feedback. And let me just give you a last overview. So if you compare this with the very traditional algorithms as we have used it in all the past, we have manual rules, we have coded logic and all of that. So it's very deterministic. Once we deployed it, it's deployed, it's trained, and then it's just as it is. And therefore the response to the market is delayed. But if you go more in that direction, what I just mentioned with that self-improvement, with iterative feedback and improving based on this, you have prompt-based memory augmented. It adapts in context and in inference. So you can also use the test time compute for this. You can use reflection. You have it online, so the test time compute evolution. And what you then have for the response to the market, it's real time and it's contextual adjustment. So given all of that, so one of my key takeaways I want to leave you with is that I think it's very clear that LLMs are no longer just chatbots. They are really becoming autonomous agents where they have reasoning, they can plan, they can use tools and have then newer capabilities. Then depending on the agent architectures, we can unlock different adaptabilities. So I've showed you the React and the reflection and the tree search, and also that kind of hierarchical setups where you can have a team of supervisors and a team of teams, very much kind of modeling a company, or at least a branch, part of the company, a department. And that models can think. So remember what I said with the test time compute, the more time you give them, the better they get. So that is with the smaller models, so they can reason, they can outperform larger ones. And with the last part I showed you, if we go down into that evolutionary agents, we can enable like continuous improvement, and we can have the agents during deployment adapting real time to shifting market conditions and adjust then the underlying strategies, and kind of from that evolutionary part become sort of a living system and aren't static anymore. Oh, this brings me to questions. Wow, a bit later than I wanted, 3 minutes later.
Hey, Nicole, thank you so much. Can you hear me?
Yes, I do.
Excellent. Good. We can't see you, by the way. I don't know if you want to
Yeah.
go back on
Yeah,
camera.
I
There we
switched that
go.
back.
Okay, excellent. Good. So, Nicole, thank you so much. We have a number of questions. Nadedo asked a few. So, Nadedo Mabalu, I'll ask one of Nadedo's questions. Can these methods elevate LLMs beyond surface level pattern matching to support casual reasoning, abstraction, and high stakes, uncertain environments like trading or portfolio management? Did I ask that clearly? Does that make sense?
I think he means kind of that different agentic setups with reinforcement learning. So yes, of course, because reinforcement learning was long or is long used within finance. And what you do now is you kind of combine both this together. So you have that prompting set up, but at the reinforcement part, and you iterate and find better solution, and you have an exploitation of different paths and different solutions. Yes.
Excellent. So Nadetta, I hope that answers your question. If you have a follow-up, feel free to put it in. Francisco asks, can you please provide a GitHub link where we can actually see the implementation of the code if possible?
Of course.
Thank you for being generous with your code. That's great. Lee Tuo, hi Nicole. What kind of LLM is used here? Is it a general commercial model or something that is fine-tuned for specific financial purposes? Thanks.
Well, for what I showed with Lux, it was, let me think, I just used GPT-4o. What I do and what I would really suggest for everyone and what I do at my company, I would never use for my application, like really production-ready application, a closed source model, because you don't control the iteration. So you should always have an open source model, see and validate. So there are different benchmarks, although I designed right now a custom benchmark specifically for us. So you might want to look even if you need a custom benchmark for your use case to evaluate the results from your models. And then you can decide if you need or want an additional data set. So there are actually quite some data sets on Hugging Face within the financial space. So then you want to train the model based on this as well.
Excellent. Okay. Lots of other great questions, Nicole. You ready for this one? You ready? Good. Okay. I'm going to read Alex's question. The high-level message of this talk seems to be pure connectionist, parenthetical, neural learning can be beaten by a connectionist plus symbolic statistical hybrid approach. Are there any other classic statistical learning applications Nicole thinks researchers should be looking into?
I mean, basically, honestly, what I would do is I would very much look into the traditional reinforcement learning parts, which is not in that sense statistical, and then in the combination with language models. I mean, it depends on the domain, but for this and for the talk, what is really interesting and important to see is that you can improve the output over the iteration or amount of iteration and feedback for the model. And depending on the tool you give it, it gets better. So all what goes into helping the model have an iterative refinement, I would look into this. And this goes all into free search, like beam search, all those classical things from computer science. And then Monte Carlo tree search and classic reinforcement learning, like PPO and all of that things.
Okay, we have a number of questions. We're going to get through to as many of them as possible. We do have just a few minutes left. Nisarg asks, are any principles from evolutionary psychology, such as innate heuristics, risk aversion biases, or social learning dynamics, built into the behavioral descriptions or learning rules of your evolutionary agents? If not yet, do you see value in adding them?
Not in those in particular, but yes, it goes in the direction. So there's actually a memory graph which learns the pattern and the behavior of a user, and based on this adjusts to, let's say, the risk appetite or the kind of the way they want the strategy and overall interaction to be. So yes, and you can very well train the models in kind of adapting to certain behavioral or psychological traits of a user.
Thank you for that. Humjai asks, learning by evolutionary agents is static at deployment, or do the agents execute online learning, in quotes?
I think we need to define this. Static, they are not static in that sense. And if that online learning refers to the paradigm for reinforcement learning and online learning, then yes, it has that interaction with the feedback. So it's not just that they get not access to the overall environment, so they learn and adapt constantly. So you have, like I said, locked into the market data, and based on this, they can refine the strategy based on this. And just to be clear, this is not hyperparameter tuning of a strategy. It's the rewriting of the code underneath. It's not just tuning some parameters.
Okay, so are you okay to take a couple more questions, Nicole?
Sure.
Excellent. So Ling asks, thanks for the presentation. In regards to longer interface time for smaller models, would you say to be a potential trade-off if, say, deployed in a high-frequency trading scenario in the future?
Look, I mean, basically what you can do, you can parallelize those things depending on the strategy you're having. Like, remember the second algorithm I showed you? You can parallelize it because it splits the trees of that beam search. And then if you parallelize this in different splits, you're still fast. And you need to think also that if you have a large model deployed, you usually have a higher latency. So before we speak from first token, which will be generated. So usually if you have that very big model, the first time to the first token takes longer than with a smaller one. And if you optimize this, and also there are different ways of even speed this more up. So you can have the cache, KV cache more, so the new tokens get produced faster. There are also advances like flash attention free, which is specifically for the later iterations of the NVIDIA GPUs, and they actually perform, if you compare the B100 with the H100, it's 15 times faster for inference than the previous one. And this is already fast. So if you combine both then together, you get extremely fast.
Excellent. Okay. And Nicole, I think lots of great questions. Sorry, folks, we're not going to be able to get to all of them. Let's end on a general one. Would you suggest, do you have any further suggestions for further resources for these agents?
Resources as in learning, or?
I seem so, or just to go for a deeper dive into them, perhaps. This was John's question. John, if you want to clarify that question, in that case, I'll tell you what, let me ask you a different question then. Maybe John can give a little more insight into that. Zulfikar, and I hope I'm pronouncing your name correctly, Zulfikar, what is the role of prompt engineering in agentic AI?
I mean, prompt engineering basically does what I was mentioning with the reasoning model. So remember when I had that distinction from the different terminology between the foundation, the language instruction, and reasoning model. So that chain of thought is a prompt engineering part. And now what we did is we implemented this also already in the training phase of the model, together with reinforcement learning. And prompt engineering, basically what this does is it helps also the model with guidance and instructing the answers, and also leveraging the in-context learning, which you can do now more in a more exploitive and organized way with the Monte Carlo tree search and the other search algorithms I showed you.
All right, and Nicole, we'll just go back to John's question since he gave a little more clarification. Yes, I'd be interested to learn more about trying and learning more about the agents. So sort of just general advice on learning more about these agents.
Mm, Let me think. I mean, I can share, just reach out if you want to me via LinkedIn. I can share a couple of repositories from me where I have things there, and this should be already a good start to get a better understanding.
Okay, and well, first of all, thank you all, your folks, for attending today. Sorry we couldn't get to everyone's questions. And of course, major thank you to Nicole Konigstein for her talk today. Nicole, thank you so much. Such a pleasure to have you today. And thank you for availing your time to us today.